Salam everybody. So I hope you guys are well. We're discussing this paper 9702/43 of the A level for October November 23. Now before you start this paper, I would only request that you have solved the paper yourself first, because I'll try to keep it as precise and as in depth as possible. But the prerequisite is that you've solved the paper and you've got lots of trouble in this paper. So let's go. Let's have a look at the first question. You have the data booklet here, and question number 1. State what is indicated by the direction of gravitational field line at a point in a gravitational field. What does a gravitational field line show? A gravitational field line basically shows, if let's say the gravitational field is this way, it basically shows that the force acting on the mass is going to be this way. And I would also want to tell you that, let's say for example, if the gravitational field is, let's say for example like this, then again, if I would turn it like this, if it's this way, then the force would also be this way. So remember that it shows the direction of force on a mass placed at a point in the gravitational field. Now explain with reference to gravitational field lines. Remember, they're talking with reference to this, so you have to mention this in your answer. Why the gravitational field line near the Earth's surface is approximately constant? Why is the gravitational field constant? It is because the spacing between the field lines should be constant. So the gravitational field lines are nearly parallel for small changes in height compared with the radius of Earth. Now this is very important that you mention this, that what do you mean by small changes in height? Look, the radius of Earth is this. So a small change in height would mean literally this. You cannot say double the radius of the Earth or double the radius of the planet. I hope that makes sense. So when you're very close to the planet, the gravitational field lines are nearly parallel, which means that the gravitational field strength will be constant. So they're asking you to comment on the gravitational field strength by reference to gravitational field lines. Now, part B, a large isolated uniform sphere has this mass. I'm sure you read the question. The radius is R, point P lies over here. And this is how the gravitational field strength varies with the distance. So they've given you this graph. And when they show that it's R and minus R, it basically means that if this is the planet, right? So either you're on this side or you are on this side. So if let's say, for example, this is plus R, this is minus R. And up to the surface, the gravitational field strength just keeps on increasing. So it's going to be maximum at the surface of the planet. Now, the magnitude of the gravitational field strength at the surface is Y. So remember, I'm using the term gravitational field strength, but they're saying gravitational field, same thing. Gravitational field strength is gravitational field. Determine an expression for Y, which is the gravitational field strength in terms of m and r square. So Y is gm over r square. Identify any other symbols. G is gravitational constant. M and R, I think they would have already explained what M and R are. M is the mass and R is the radius. So you don't need to mention that. You only need to explain this. Explain why at the surface of the sphere G always has the opposite sign to X. Now X is pointing outward. Why does gravitational field always point inward? The answer to that is very simple, and I've explained it in this way, that gravitational field strength is always attractive, right? It pulls you in. So gravitational fields are always attractive, hence inward pointing, and the force is always opposite to your displacement. X is your displacement. So if you move something from here to here, and this is the planet, where will the gravitational force point? The gravitational force will point inwards because it's always attractive. So force is opposite to displacement. Now complete figure 1.2 to show the variation of gravitational field strength for a distance up to plus minus 3r. Now you know that G and r square have an inverse relationship, right? And let me see if I made a table for you. Yes, I made the table for you. So look, G and r squared have an inverse relationship. What does that mean? Always make this table. That when the distance is 1r, the value is going to be 1g. When the distance is 1, the first row is always fixed. Now let's come to the second row. When the distance is 2r, what will be the value of g? In terms of g, answer the question. In terms of g. So G is inversely proportional to R square. When you say 1 over 2 R, you're basically doing 1 over 2 square, because basically the radius or the distance has doubled. So it's 1 over 2 square. 1 over 2 square is 0.25. So the gravitational field strength goes down to 0.25 G. Similarly, write down 3R. And what is the gravitational field strength? Again, you have the formula over there, which is 3R. So if you do 3R whole square, what is 1 over 9? 1 over 9 is 0.11. So the gravitational field strength decreases to 0.11 G. So similarly, try this yourself and let me know in the comments what will be the value if I write, 4R over here. Let me know what should be the answer. So, but they've said up to 3R, so we're going to stick to 3R. I have labeled the points for you. If you can see, this is 0.25. So 0.25 at 2R, and this is going to be 0.11 roughly. And similarly, minus 0.25 over here, and this is minus 0.11. And because it's an inverse square relationship, so hence it's a curve. It's not a straight line. So that's why you have this curve. So you mark these points and you make the curve. Done. Question number 2. Define specific heat capacity. This is the amount of heat required to change the temperature. Remember, you have to change the temperature. It's not necessary that you always increase the temperature. You could also decrease the temperature. So when you're writing the definition, you always say to change the temperature of a unit mass by 1 degree Celsius or 1 Kelvin. An ideal gas of mass 0.35 kg is heated at a constant pressure. So the pressure is given, the mass is given, so that its internal energy increases by 7,600 joules. Interesting. So somewhere laws of thermodynamics. During this process, the volume of the gas increases 0.038 to 0.063, and the temperature increased by this. Work done. What is the formula for work done? Work done is pressure times change in volume. So you have the pressure, which is 2 10 per 5, which you will plug over here, and then you have the change in volume, which is this minus this, which you do over here, and you will get your answer as 5,000 joules. Explain whether the work done on the gas is positive or negative. So is the gas expanding? Yes. When the gas is expanding, what does that mean? It's work done by the gas, and work done by the gas is always negative. Why? Because whenever you write down your law of thermodynamics, it's this, and this W is representing work done on the gas, and on the gas always means compression. So here they've given you the words clearly and the numbers that the gas is expanding. So it's not compressing, it's the reverse. So it's work done by the gas. So work done by the gas has to be negative. Now, determine the magnitude of the thermal energy transferred. So delta U is equals to Q plus W. 7,600 was the increase in the internal energy, was given over here, 7,600. You've calculated this 5,000. Now this 5,000 will be written with a negative sign because this was work done by the gas. So your final heat supplied will be 12,600, and use your answer to calculate the specific heat capacity. So Q is equals to MC delta T, as you can clearly see. Q is the heat supply, 12,600, mass is 0.35, specific capacity is C, and the change in temperature is going to be 56. So C is going to be 643. Now, what are the units going to be? This is in joules, this 0.35 was in kgs, and 56 could be, because this is temperature change. Remember that temperature change in degrees Celsius would be equal to temperature change in Kelvin. So either, and if you look at my units, so you could write joule per kg per degree Celsius, or you could write joule per kg per Kelvin. I hope that makes sense. For part C, Bismillah. So for part C, if you read the question, I'm sure you've already read it. They say that the volume is constant. So that means that your work done, which is pressure times change in volume, this is 0. And when your work done is 0, then Q is equal to delta U. And they're saying that the increase in internal energy of the gas is the same as in B. So the increase in internal energy initially was 7,600, and it is the same. Now just imagine the value of Q that you need. Would that be 12,600 or would that be 7,600? It will be 7,600. Why? Because now there's no work. So the value of Q has gone down. The amount of heat that you're giving has gone down. So the amount of heat given has reduced, number one. I hope that makes sense. Number two, you all know that your internal energy is proportional to your temperature for an ideal gas, because potential energy between the molecules is zero. So the internal energy is purely kinetic, and kinetic energy is dependent on temperature. So just remember that for an ideal gas, your internal energy is directly proportional to your temperature. So the increase in internal energy of the gas is the same. Now you all know that your internal energy is given by this expression. Let me write that down over here. Your internal energy is a sum of your kinetic energy and potential energy of the molecules of the body, but because you're talking of an ideal gas, so for an ideal gas, your potential energy is zero. So internal energy is purely kinetic. And if you want to change in your internal energy, then your kinetic energy must change. I hope that makes sense. And what is kinetic energy dependent on? Kinetic energy is dependent on temperature. If you want to change your kinetic energy, your temperature must change. So if you mix the two relationships, your internal energy will only change if your temperature changes. And now what are they saying? That this is constant, which means that the change in temperature is also constant. Make sense? So we've already decided that the amount of heat that you need to give should be less. It should be 7600. Previously it was 12,000 something. Now it's 7600 because there's no work. And furthermore, we're also saying that your temperature change is also constant. So temperature change is constant. Mass is constant. Can I say Q and C have a direct relationship? Of course. So if Q is less, what should happen to C, the specific capacity? It should also be less. Mark this in your notes. It requires you to manipulate some equations and then use your brain. Very good part. Moving on. Question number 3. Ideal gas. The product PV of an ideal gas is given by this expression, 1 by 3 nm mean square speed. What is N? N is the number of molecules. M is the mass of one molecule. And mean square speed is C. Use the equation for an ideal gas to show that this is the expression. You should know this. How do you derive this? You know PV is equals to NKT. This is an equation for ideal gases. Now PV is equals to NKT and PV is also equal to this. So I can say that these two things are equal. And that's exactly what I've done here. NKT should be equal to 1 by 3 nm mean square speed. And I've done this in steps, but you could do it here as well. You could just cut out the ends and you could take this 3 to this side. So basically you will get 3 kT is equals to mc squared. What I'm saying is you could just cut out these ends and you would get 3 kT is equals to m into mean square speed. Now what you do is, because you want kinetic energy, so you need half mv squared. So what do? You multiply 1 by 2 over here and you multiply 1 by 2 over here as well. So what is this thing? This thing is your average kinetic energy, which is this thing. And this is 3 by 2 kT, which is here. And remember that this is the average kinetic energy of a single molecule. What if they ask you for, but it's not asked over here, but what if they ask you for the total kinetic energy of the gas? Remember, it will be 3 by 2 NKT. Just add this if you've done this question. If they ask you for the total kinetic energy of the gas, this is the average. So this is for a single molecule. If they ask you for the total kinetic energy of the gas, that will be 3 by 2. And where will this be used? This total energy? This total energy can be used in this equation. Delta U is equals to Q plus W. They can give you a question in which they could ask you to tell us what is the internal energy of the gas. The internal energy, as I explained in the previous part, is directly proportional, or you can say it is equals to your kinetic energy plus potential energy. For an ideal gas, this is 0. So your internal energy is purely kinetic. So this is 3 by 2 NKT. Now you use NKT over here. Why? Because this represents the whole gas. Remember this. This delta U is for the whole gas, not one molecule. So the total kinetic energy can be used in replacement for delta U for an ideal gas, and then it can give you Q and they can ask you to find W, etc., etc. Multiple questions can come. Part B, the surface of a star contains or consists mainly of a gas that may be assumed to be an ideal gas. The RMS speed is 9,300. The mass of the molecule is this. Determine with 3 significant figures the temperature of the star. So they've already made you derive this result, right? So half mv squared should be equal to 3 by 2 kT. So 1 by 2 mass is given 3.34 10 to the minus 27 into mean square speed. That's 9300. So you put that over here is equal to 3 by 2 K. K is Boltzmann constant. The value is given in the data booklet. You can check it. You find out the temperature. The temperature turns out to be 6977.6. You can write that as 6980 kelvins. And one thing that I have to mention over here, that they've given you the RMS speed. Now remember that RMS speed is the square root of your mean square speed. So what is your mean square speed equal to? It's basically C RMS whole square. So 9300 is this one. So your mean square speed will be 9300 whole square. Got it? I hope that makes sense. This was the RMS value. So RMS value is square root of your mean square speed. Remember the words. This is root mean square and this is mean square. And in this formula, you have mean square. So you have to find out what is your mean square speed when you know that this speed over here is 9300. Just square both sides and you will know what your mean square speed is. Plug that here and get your answer. Part C, the radiant flux intensity. Ooh, so what they've done is, if you look at the question, they have merged ideal gases with astronomy. Radiant flux intensity of the radiation of the star is this. When the distance is that, calculate the luminosity. Easy question. You know the formula, L over 4 pi d square. They've given you the distance. You want to calculate the luminosity. Luminosity is your power. So when you do all of the math, I've plugged in the values for you over here. You get 5.5 in 10 to the power 26, and the unit is watts. Remember, that's why I told you it's very important that you do the paper before you look at this video. And if you haven't done and you're here, please, 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 you want to ace your exam? You have to solve it first yourself, and then wherever you get stuck, come back to the video. But first, solve the whole paper. And remember that the number of questions are 10 and you've got 2 hours. So in 1 hour, you should be done with 5 questions. If you're not done with 5 questions, you're in trouble. So your speed should be such that you're able to do at least 5 questions in 1 hour. And it's draining. It is. So remember that you have to do it with focus because you won't have the time to recheck. Remember this. This is not O-levels. What is the radius of the star? You know the formula is L is equal to sigma A T raised to the power 4 because A is 4 pi r squared, which is going to be the radius of the star. So your luminosity is given over here. This is Stefan's constant, 5.67 times minus 8 given to you in the data booklet. The temperature was something that you already figured out over here, 6980. So you plug, chuck, and get the answer. The gas at the surface of a star has a very high pressure. Use the basic assumptions of the kinetic theory to suggest that why in practice a gas at the surface of a star is likely to behave as a light. So just look at what they're assuming. A lot of kids get stuck at in these last parts. So either you can get your answer through equations, or you can get your answer by looking at what they're assuming and you can challenge that assumption. If they're asking you why something, so the answer lies mostly in the assumption. What they're assuming is that the surface has very high pressure. Now imagine if the pressure is very high, that is obviously not ideal. So when the pressure is high, the molecules will be close together, intermolecular forces will be strong, potential energy will exist, and so many times we repeated in this one little video that for an ideal gas, potential energy has to be 0, intermolecular forces have to be negligible, which is what you assume for an ideal gas. Hence, it is unlikely to behave as an ideal gas, and that's exactly what you've written here. Question before. A heavy metal sphere of mass 0.81 kg is suspended from a string. Okay, this is question of SHM. What is meant by SHM? SHM definition. Acceleration is proportional to displacement and is always directed towards the mean position. You can remove the word always, but the definitions here. And remember that the definitions are free marks. If you're losing marks in definitions, you're going to really seriously jeopardize your grade. So just remember that definitions have to be memorized. And there is no question that you go wrong. No matter whether you like the subject or not, no matter whether your numericals go right or not, definitions have to go right. Remember this. And there's no pardon for anyone who says, I don't remember the definition. That's the most basic thing. And there's so many free marks that you can just score by just knowing the definitions. Calculate the angular frequency. So angular frequency omega is 2 pi over t. Do we have the time period? Yeah, we have the time period, which is 3 seconds. So 2 pi over 3, which is 2.09, and you get 2.1 meters per second. What is the total energy? The formula for total energy, the formula for maximum energy, total energy. Remember, if they ask you what is the maximum kinetic energy, what is the maximum elastic potential, whatever, maximum energy, total energy, all have one formula, which is this one, half m omega square a square. So you just plug in the values and you will get your answer as 2.3 × 10⁻³ I've done all of the working, and I've checked these calculations, so just check them out as well, but do it yourself. I've done this myself, so you also do it. Part C. The suspended sphere is now lowered into water. The sphere is given a sideways displacement. Okay, so you put it in water and you displace it sideways. Just picture it. You displace it sideways. Will it be able to make complete oscillations? No. And they're saying that the water causes the motion of the sphere to be critically damped. So there should be no oscillation. Critically damped means that your swing dies out in the least possible time. On figure 6.2, sketch the variation of the displacement from t is equal to 0, t is equal to 6. Now, if you remember that they had already mentioned that the time period is 3 seconds, let me explain it over here. If it's 3 seconds, that means you start from here, you go here, and you come back in 3 seconds. That means one motion. Let's say you start from here, and you just go this way, this should take 1.5 seconds. That means that just going from here to the middle position should take 0.75 seconds. And if you're damped, critically damped, you will basically come from here, you're going to probably cross the mean position because this is where your speed is maximum, but then you're going to massively slow down and you're going to stop. If you're critically damped, if it's light damping, what is the difference between critical damping and light damping? In critical damping, if this is your amplitude and this is your time, in critical damping, you basically go down like this. This is critical, and what is light? Light is this. It takes you an infinite amount of time to come back to your equilibrium position. And what is so this is critical. This is heavy damping. Sorry, this is not light damping. Heavy damping is in which you take infinite amount of time to come to rest. And what is light damping? Light damping is this, in which you have clear oscillations, and this is something that happens usually in your in most of the oscillations in real world when you are doing pendulums in class or in lab. That's light damping. So this is light, heavy, and critical. But this is the first time actually that they've asked you to draw a graph of critical damping, because usually they ask you for light damping and you just make clear defined oscillations. But over here, because they've asked you to show critical damping, so you have to make sure that you start from that amplitude of 0.036, because that's what they mentioned over here, that the amplitude is 0.036. So you start with that amplitude and then you decrease it. Like I said, that 0.75 second point has to be crossed because that's your mean position, and then you die out in your least possible time. So you could do it like this, you could do it like this. That's completely fine. All right, and just don't show any oscillations. And that is question number 4. Question number 5. Define electric potential at a point. Work done per unit positive charge in moving it from infinity. Again, it's a definition. Free marks. Rote learn it. 2 isolated charged metal spheres, X and Y, situated next to each other in a vacuum with their centers 24 meters apart. Okay. And point P is a variable at a variable distance. And okay. This is the potential versus resistance graph. So what is the instant reaction that I can get from here? Instantly, I can say that because the potentials are in opposite directions, that means that one of them is positively charged and the other is negatively charged, because potential is scalar. So if potential is in between positive and negative, that means that the spheres are oppositely charged. And can you see that the overall potential is 0 at x is equals to 12? What does that tell you? The total distance was 24 between them. Between the two squares, the difference was 24 meters. And right at the center, the potential is 0. Right at 12 meters, the potential is 0. That means that the charges were of the same magnitude. And just one more thing that we can conclude, look at the flat line. You know that the potential is constant within. So if you look at the flat line over here, it's smaller. If you look at the flat line over here, it's larger. That means that this sphere is larger and this sphere is smaller. This flat line represents the radius of the sphere. So the spheres are of different diameters or different radii, oppositely charged, different diameters, and the magnitude of the charges are equal. A positive charge particle is placed at point P, such that x is equal to, so okay, you place it at the middle. Describe and explain the subsequent motion of the particle. So you can safely say that, let's assume that this is x and this is y. Let's say this is the negatively charged one and this is the positively charged one. So what's going to happen? What's going to happen is, if you've placed a positive charge over here, the positive charge will be attracted towards the negative charge and will be repelled by this positive charge. So that's exactly what we're expecting. So charge y repels P and charge x attracts P. And the reason for that is they've already mentioned that x and y are two charges. And so we're assuming that charge x is the first one, which is this one. And this is the second one. And charge y repels P, charge x attracts P, hence force is towards x. Like I said, it's one way. The force increases as distance x decreases. So they already mentioned that point P is at a variable distance x from the center of sphere x. So this is sphere x, and sphere x is negatively charged. So you can just imagine that if P is getting attracted, what's going to happen to the distance x? First x was this much, then x is this much, then x is this much, and what's going to happen more? Imagine you're getting pulled and you're getting closer and closer to the opposite charge. What's going to happen? Your speed will increase, your acceleration will increase, your force of attraction will increase. So those are all the things that you have to mention when you're explaining the motion. So charge y repels P, charge x attracts P, hence force towards x. The force increases as distance decreases, because we know that the force is inversely proportional to distance squared. That's Coulomb's law. Hence the speed of P increases towards x. You can say the acceleration of P increases towards x. And oh yeah, I've explained that over here as well. Brilliant. Question number 6. Define magnetic flux density. Definition. Rote learn. Magnetic flux density, remember the formula is F over IL, and when you're defining, you write sine 90. So F is force, I is current, L is length, theta is the angle between. So if, just to give you an idea, if let's say this is the magnetic field, let's say this is north and this is south, and you have a conductor over here, then the angle is 90. And if your conductor is placed like this, then this is going to be the angle. It's the angle between the length of the wire and the magnetic field. So it is, how do you define magnetic flux density? It's defined as the force per unit length, because it's F over L. Per means divide. So force per unit length acting on a current carrying wire. You could also say force per unit length per unit current. That's also fine. Or you could say force per unit length acting on a current carrying wire. Actually, I've mentioned per unit current because I need to mention that it's that the current is in the denominator. So force per unit length acting on a current carrying wire per unit current placed perpendicular to the magnetic field. So remember that you have to explain this. So if it's completely fine if you just write this down. You write this down over here and you explain this to us. You're good. You're sorted. Because you have explained that the force is per unit length, per unit current. You're just trying to explain the formula in words. So just find out what's easier. I've done both because I wanted to do both. But you guys do what you feel better. But remember that when you're defining, you're explaining the formula. Part B. Electrons are moving in a vacuum with a speed of 1.7 10 to the power 7 meters per second. The electrons enter uniform magnetic flux density, field of flux density 4.8 milliteslas. So this is a field. Whoa, you can't see it. I can see it. So the field is over here. Actually, let me mark the outline for you. The field is here, and this is a uniform field of 4.8 milliteslas. An electron comes in and it turns this way. And why does it turn this way? Because there must be a force acting towards the center of the circle. And the force is downwards. I don't need to apply any rule for that. The reason for that is, why is the charged particle going down? It's because it's experiencing a downward force. That's why. So the force of the magnetic field on the charged particle is this way. I can actually find out what is the direction of the magnetic field, because if the electron is going this way, then the current has to be in the opposite direction, and then you can just use Fleming's left-hand rule to figure out what the direction of the magnetic field will be. Do you want to do it? Left hand, current should be, oh, this is giving you the, it's giving you the mirror image. It should give you the mirror image. I can't do mirror images right now, but let me just do it with my hand over here. So let's say this is my. Can you see this? Yeah, you can see this. I'm gonna do it on my page. So the current is this way. Second finger showing current, and the current is going to this side over here. Force is downward, so my magnetic field should be into the page. Current is this way, force is downwards, force is towards me, magnetic field should be into the page. Let's see if they ask you that. Oh, actually they haven't mentioned. State the direction of the magnetic field is into the page. And if they ask you to explain it, magnetic field is into the page because Fleming's left-hand rule, and you just write Fleming's left-hand rule. Show that the force has this magnitude. So the formula for the force is QVB, force on a moving charge. You know the charge on the electron is 1.6 10 to the minus 19. The velocity was given to you in the question, 1.7 in 10 to the power 7 over here, and the strength of the field was 4.8 milli, so milli is 10 to the minus 3, and the force is 1.3. And this force also provides you with the centripetal force. And what is the direction of centripetal acceleration? It is the same as the direction of the centripetal force. Use the information B2 to calculate the distance d between the path of the electrons entering and the path of the electrons. So they're asking you for this distance. So magnetic force provides the centripetal force. You can find out what the radius is, and then you can double the radius. So F is equals to Fc. You already have the magnetic force. It provides you with the centripetal force, mv squared r. You have the mass in the data booklet, 9.11 10 to the minus 31. You have the velocity given to you in the question over here. And you just rearrange, take r to this side, 1.3 10 to the minus 14 comes down, and you know the answer. This is 0.020, but they're asking you for the distance d between the path entering and leaving. So they're asking for the whole distance. So you have to double it, and your answer is 0.040. And if you made the mistake, like when you were doing this yourself and you wrote 0.020 over here, just don't bash yourself too much, because look, you're under pressure. Just remember to read the question carefully, okay? And that's going to help you a lot. The electrons will be replaced with positrons, positive charge, same mass, that are moving with a speed 3.4 in 10 per, so double the speed. Along the same initial path, the positrons enter the magnetic field at point X as well. And you have to draw a line to show the path of the positron. So they're entering along the same path with double the speed. Now you know that r, the radius, is mv over bq, the radius of the turn. But that's what you just figured. The mass is the same, magnetic field is the same, the charge sign is opposite, but the magnitude of the charge is the same, so radius is proportional to your velocity. So if you're doubling the speed, your radius will double. And because your charge sign is reversed, so instead of electrons, you have positrons. Positrons are positively charged. So that means that the current will be this way. So remember when I did this I hope you can see my screen. Yes. For electrons, my current finger, the second finger, was pointing this way. But for positrons, it should be this way, in the opposite direction. Now the force is going to be up the page. First it was towards me, now it's going to be away from me, because the current direction has been reversed. And I should have done this over here. Yeah, I've done it over here. So with positrons, if you want to do it, if you have positrons coming in from here. Remember, positrons are positively charged, so your current finger, your second finger should be pointing this way. Magnetic field is into the page, as you know. They haven't changed that. So just figure out the direction of the force, and the direction of the force will be upwards. And remember that the radius has to be doubled, which means that what I did was I calculated this distance d, and I took the same distance and I doubled it. So I knew, because the speed is doubled, so this distance has to be doubled. So it's going to be upwards, circular, and doubled. And you show the path. And that is the answer. Question number 7. AC. A varying current is passed through a resistor R. And you can see that the current fluctuates between minus I naught and 2 I naught. And the time period is like this, from here to here. This is one wave. Now, determine with an expression for the power dissipated. Now, power dissipated is I square R, but as you can see that the current is oscillating. So determine expression for the times when the current is in the negative direction. So they specified in the negative direction. So in the negative direction, it's P is equals to I naught square R. In the positive direction, it's going to be this current. So 2 times I naught whole square, because the formula for power is I square R. So in the negative direction, you basically pick up this current. In the positive direction, you pick up this current. So 2 I naught square R, 4 I naught square R. And what is then, how do you sketch this? So power dissipated will always be positive. It can't be negative. And you have to label the power axis with an appropriate scale. So what I did was, this was 0, 0.51, 1.52. So I did it like this: 1 I naught square R, 2 I naught square R, 3 I naught square R, 4 I naught square R. So because I know that I had to go from I naught square R to 4 I naught square R. And then you also have, this thing that it's I naught for the first 0.5 t. So it's I naught square R for the first 0.5 t. Then for 2 I naught, it's 0.5 to 1 t. So for 0.5 to 1 t, it's going to be 4 I naught square R. This is the power. And that's it. Then you keep on fluctuating it, and then you join them with the transitions. More important point is that the power will always remain positive. Next is, what is the mean power dissipated? Mean power dissipated is the average. So this is your maximum, this is your minimum. Just take the average. I naught square R plus 4 I naught square R divided by 2. So you get 2.5 I naught square R. And what is the root mean square current in the resistor? So root mean square current, for that you first need to find out what is your average of, look at this. IRMS is root of the mean square current. Now what is your mean square current? Your mean square current minus I naught, if I convert it to I square, I will get I naught square. And this 2 I naught, if I convert it to I square, I will get 2 I naught whole square, which is 4 I naught square. So what is my mean square current? That's going to be I naught square plus 4 I naught square divided by 2. Remember that this is root mean square. So first you square. So first I squared the two different currents. Then you take the mean. So I took the mean, and I ended up getting 5 I naught square divided by 2, which is 2.5 I naught square. And now you take the root, so you do an under root on this to get IRMS. And that's exactly what I've done over here. So I took the mean square first, square, then mean, this, and then root on top. So square root of 2.5 I naught, and you can get the answer. And it was actually 2.5 I naught square. So because this is I naught square and this is an under root on top, so under root and I naught square will get, the square will get cancelled. So you'll have I naught outside, and under root 2.5, you can just do it in your calculator and you get the answer. I hope that makes sense. Question number 8. Show that the momentum, very common question. Show that the momentum of the particle is given by this expression. So you all know that E is equals to mc square, right? I can break that down. I can write it as E is equals to mc into c. mc is momentum, so E is equals to P into C. You also know that the energy of a photon is given by hc over lambda. So hc over lambda should be equal to P into C. C and C will get cancelled, so you get P is equals to h over lambda. Multiple ways to go about, but this is the way that I do it. Use the expression A1 to show that the photon has this momentum. So you have the values already. You have this momentum, and you know that the value of H is 6.63 10 to the minus 34, which should be divided by lambda. So I haven't done it. Let's do it right now. So lambda should be 6.63 10 to the minus 34. I just assumed that that would be the answer. Divided by 9.5 into 10 to the minus 28. And yep, I'm getting 697 into 10 to the minus 9 meters, which is 697 nanometers, which is red light. Because red light is VIB GYOR, that's the spectrum. This is 700 nanometers and this is 400 nanometers. So red is 700 nanometers. A beam of light, red light, has this intensity, 160 watts per meter square, incident on a surface. The momentum of each photon is this. All of the light is bounced back or reflected back to its original path, and the cross-sectional area is 2.5 into 10 to the minus 6. Show that the number of photons incident on the mirror per unit time is this. So it's something has to do something with intensity. The number of photons. So intensity is power over area, correct? And if I break down power, I get energy per unit time, correct? And now, because there's not just one photon, there are many photons, so you have to multiply this with n to get the total power of the incident photons. So the total power is basically Ne over T. When you divide this total power by the area, which is this, so you get Ne over At, which is the intensity. And now they're asking you for the number of photons per unit time. Why are they asking you for per unit time? Because they're not giving you the time. So they're wanting you to find out this value, N over T. N over T would be current into area over the energy. Do you understand? So you have, not the current, the intensity. So the intensity is 160. The area was 2.5 into 10 to the minus 6, they've mentioned over here. And you have to divide this by the energy of the photon, and they should give you the energy of the photon. Have they not given you? That's fine, we can find it out. The energy of the photon, because they've given you this expression, lambda is, where is it? Lambda is H over P, or E is PC. E, energy of the photon, is PC. Do I have the momentum? Of course I do. 9.5 into 10 to the power minus 28 into speed of light, 3 into 10 to the power 8. This is the energy of the red photon. So the area multiplied with the intensity, then divide by the energy on the other side as well. And the energy is this, and I get 1.4 in 10 to the power 15. This is the number of photons per second. Use the information B1 to determine the pressure exerted. Now, remember this, that when you're talking of pressure exerted, pressure is force over area. Somehow we need to understand how do we get force. We have the area. So force is rate of change of momentum, because I guessed from here, because why are they giving you the momentum? And why are they telling you that it's the opposite? So it's something to do with AS. So force is rate of change of momentum. Again, remember that this is for 1, so you have to multiply it with n. And the change in momentum is this much. The change in momentum is going to be your final momentum minus the initial momentum. That's a very important thing, into N over T. N over T you've already figured. That's the number of photons striking per second. The change in momentum, now you know that your initial momentum was this way, your final momentum is this way. When you calculate the change in momentum, it's a vector quantity. So when you do PF minus Pi, you will have to put a negative sign again, because momentum is a vector quantity, so one direction has to be positive. You must remember this from your AS. Or you could do it like this. You could take this direction to be positive. Momentum is a vector. This is true for any vector quantity, just like you would do for velocity. So this momentum is positive, this is negative. So change in momentum is final minus initial momentum, but you must understand that the two vectors are in opposite directions, so one of the vectors will have a negative sign. So it's actually going to be Pf plus Pi, and because the momentum is the same, so you can say 2 times Pi, 2 times the initial momentum. So your initial momentum was 9.5 × 10⁻²8. So to calculate this, you will do 2 times the initial momentum into n/t, and that's exactly what I've done here. So look, this was n/t. Okay, this was n/t, and to calculate change in momentum, I did twice of the momentum, and I got the force. Then once you get the force, you divide the force by the area, and you get the pressure, which is 1.06 × 10⁻⁶, or 1.1 × 10⁻⁻6 pascals. The beam of red light is now replaced with a beam of blue light of the same intensity. What's the difference between blue light and red light? Where is it? Here it is. Blue light has lesser wavelength, so blue light has more energy. But they're saying, very important thing, the intensity is the same. So intensity, as you all know by now, is the number of photons per unit time into energy over the area. Intensity is the same, but you have increased the energy because you're using blue. So blue has more energy, less wavelength. So the number of photons per second arriving for blue should be less. That's the first thing that you should be thinking about. So the number of photons striking per second or less. Suggest and explain whether the pressure exerted by the beam of blue light is the same, less, or greater than the pressure exerted by the beam of red light. Now, when you think of this, the number of photons striking are less. The number of photons per unit time striking are less. The energy content is more. So should the pressure change or should it remain the same? The pressure should remain the same because your energy is more, but you've got fewer number of people. It's just like this. I've got this wall and I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 workers. These 10 workers strike this thing and break down the wall. Okay. Now I'm saying it's the same wall, but now I've got fewer workers. So these fewer workers, will they need more energy or less energy to break the wall in the same amount of time, and it's the same area that you're covering? So the answer is they will need greater energy because they are fewer. But if they're doing everything, it's just like having very efficient workers. The number of people per unit time are less, but they've got more energy. So are they having the same effect? Yes, they're having the same effect. So should the pressure be the same? The pressure should remain the same. Because look at this, the intensity is the same. Hence the pressure that they're exerting on the wall has to be the same. But you have to explain this. So blue light has a shorter wavelength, energy is greater, hence the number of photons emitted per second are less. N/t is less. But their energy is more. Momentum is greater. Because their energy is more. Hence the pressure will be the same. No change in the pressure. Question number 9. What is meant by nuclear fusion? When two small nuclei join together to form a larger stable nucleus. Whenever they give you a graph of binding energy per nucleon versus nucleon number, you should always remember that it is like this, and the turning point is at 56, which is iron 56. Point X, which should undergo alpha decay. Alpha decay is for heavier particles, and undergo nuclear fusion. Nuclear fusion should be for lighter particles, so the particles at the very bottom over here. A nucleus Z undergoes nuclear fission to form strontium 93 and xenon 139 according to this way. Now, I need to explain this. Look, whenever you look at this, this is the equation of a particle. One particle of Z collides with one particle of a neutron, one neutron, forms one particle strontium. Particle could also be called nucleus because particle is atom, atom के अंदर एक nucleus. So this is a particle equation. Get this in your head. One particle of Z, one neutron, bang, xenon, one particle, strontium, one particle, and two neutrons. So you have 5 particles over here. No, sorry, 2 plus 1, 4 particles over here, and you've got these two things. This is a particle equation. And the data that they give you is always for particles. Look, nucleus, one particle. One particle of strontium has this binding energy. One particle of xenon has this one particle. The fission of one mole, one mole. Is 1 mole one particle? No. What is 1 mole? 1 mole is 6 into 10 is power 23 particles. 6 into 10 to the power 23 particles release this amount of energy when this reaction happens. So the first thing that you need to do is one Z forms one strontium. So if you have got 6 into 10 to the power 23 Zs, how many strontiums would be formed? 6 into 10 to the power 23. So what do you do with this binding energy? You multiply this with what? With 6 into 10 to the power 23 to get the binding energy for 1 mole of strontium. And similarly, one particle of Z forms one particle of xenon. So 6 into 10 to the power 23 particles of Z would form how much? 6 into 10 to the power 23 particles of xenon. I'm explaining this in terms of particles because you will get different questions. And this is something new. They want to confuse you with moles. But as long as you're very clear on the equation and the data, you cannot go wrong in this question. Understand this and try doing some other question with this logic, and inshallah you will be able to get the right answer. Determine the binding energy per nucleon. They're asking you for one per nucleon, per one particle. They're asking you for the binding energy per nucleon of one particle of C. So first of all, we need to figure out that this is the binding energy given to us when 6 into 10 to the power 23. Binding energy, what is the formula? The binding energy is always the binding energy of the products minus the binding energy of the reactants. So binding energy released is given to us as 1.77 10 to the power 13. The first thing you do is the products are these two. You've got the binding energy for 6 into 10 to the power 23 particles for each. So binding energy of products, meaning add the binding energy of this and the binding energy of this, total for 6 to 10 to the power 23 particles, because this is for these many particles. So if you do it in your calculator, multiply this with 6 into 10 to the power 23, you should get this. Multiply this with 6 into 10 to the power 23, you will get this. Add them because the binding energy of the products has to be calculated minus the binding energy of the reactants. That will give you the binding energy of the reactant to be 1.6 to 10 to the power 14. Ask yourself one question very quickly. Is this the binding energy for one particle or 6 into 10 to the power 23? What is the answer? It is for 6 into 10 to the power 23. What do you want? You want the binding energy of one particle. So go. This is the binding energy of one particle of Z. Now go to the question. What is binding energy per nucleon? This is binding energy per nucleon is basically the binding energy of one particle divided by the nucleon number. This is something that you know. This is the formula for binding energy per nucleon. But first you need to find out what is the binding energy of one particle. So you found out the binding energy of one particle to be this. Now what is the nucleon number or what is the mass number of Z? You've done O-level chemistry. So you know that this is 1. I don't know what this is. I don't know whatever this is. Call it A. So 1 plus A should be equal to, the mass numbers have to be conserved. So 1 plus A should be equal to 93 plus 139 plus 2 times 1. And that's exactly what I've done here. 1 plus A should be equal to this. So A is 233. So this is 277 in 10 to the minus 10. You divide that by 233 and you will get 1.18 in 10 to the minus 12 joules. But they're asking you in mega electron volts, so you need to know the conversion. Again, something which you should learn by heart. 1 mega electron volt is 1.6 in 10 to the minus 13 joules. So what is the value of these many joules in mega electron volts. Just do the math and you'll get 7.4 mega electron volts. And last question. Ultrasound and X-rays are both types of waves that are used in medical diagnosis to form images, blah, 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 blah. What is the method of production? These are rote learning questions. You have to rote learn them. Ultrasounds are formed by the vibrations of piezoelectric crystals and piezo crystals, and X-rays are formed when high-speed electrons strike a metal target. What are they detected? Are they absorbed, reflected, or transmitted? Ultrasounds are reflected. X-rays are transmitted. In an X-ray, the screen is behind, and the X-rays just pass through the body, and whatever is transmitted is captured. For ultrasound, the probe is just at one place. Ultrasounds go in the body, reflect back. So that is the mechanism. For one type through the tissue, the wave has 72% of its initial intensity pass. 72% of its initial intensity after it has passed. So this is, try to understand that this is your 72% of your intensity has passed. So this is transmitted. Transmitted intensity is 72% of the incident intensity. That's how you, incident intensity, look, this is the tissue. The intensity that came in was I naught, and the intensity that has passed is definitely less, so it's 72%. So this is your transmitted density, and you should know the formula, which is IT is equals to I naught e to the power minus UX. So IT is 72% of I naught, so that's 0.72 I naught. 72% is 0.72 is equals to I naught e to the power minus UX. You have the thickness, which is 6.2. You get rid of the I naught, and then you should know how to get rid of this E. You have to take natural log on both sides. Otherwise, you can see a video on my YouTube channel. You'll figure it out from there, how to take natural logs. So natural log of 0.72 should be equal to minus UX comes down, ln E. ln E is 1. So minus 0.328 should be equal to minus U to 6.2. And from here, you get the value of U as 0.053. By the way, they can ask you one question. And you know what that is? They could ask you, if 72% of the initial intensity has passed through, what was the intensity or what was the percentage absorbed? Can you answer this question? Simple question. I send an I naught, 72% goes through. What is the amount that has been blocked? What is the percentage absorbed? You will say, I sent in 100%, out of which 72% went out. What is left? 100 minus 72. It's a very typical question that they're asking these days. So just remember. So if they ask you for this question, the answer to my question was 100 minus 72 is the percentage absorbed by the tissue. Okay. Another wave of the same type in B1 passes through another thickness. Calculate the percentage of the initial intensity that is attenuated. Attenuated ka matlab absorbed. Attenuated means absorbed. Absorbed by the tissue. Now the formula has nothing to do with absorption. Nothing. The formula is for transmission, the thing that goes out. So 9.3 centimeter of the same tissue. So you have the same U value. You have a different thickness. So you get IT over I naught, which is 0.61. I naught is the initial intensity that goes in. IT is what goes out. So because they're asking for a percentage, they can also ask you for fraction. This is fraction. So if you want percentage, I will say 61% leaves. So what stays behind? What is attenuated? What is absorbed? It's going to be 1 minus or 100%. If you're using 0.61, you can do 1 minus 0.61. If you're using a percentage, just do 100% was sent in. 61% went out, but the same logic that I was explaining to you over here, 100% was sent in. 60 something percent was sent out. What is the percentage absorbed? It's 100 minus 61, which is 38.9 or 39%. And that's it. Best of luck.